for the introduction and also for the kind invitation to join this seminar series. It's a pleasure for me to give this seminar. Of course, it would be much nicer to have a chance to meet in person, but okay, in this time of COVID, that's the best that we can do. So you see from the title that I will discuss the application of so-called generative neural networks to boost the performance and accuracy of both classical and quantum Monte Carlo simulations. And here on the bottom left, you see the list of collaborators that work on the different projects that I will describe. The first is Benjamin McNaughton, a PhD student here in Camerino, who performed a substantial part of the work on the classical part. And then you have Andrea Parali, a colleague here in Camerino, Piaggio Pieri, who was previously here in Camerino and then moved to the University of Bologna. We have Milorad Milosevic from the University of Antwerp. And then there are also some colleagues from my old collaborations from the times where I was in Trieste. We have Estelle Maeva-Inac, who then moved as a postdoc to Perimeter Institute. And here also some people from CISA and also a colleague from the University of Padua. Okay, so let's move to the next slide. So here you have a scheme that is somehow a sort of outline of this presentation. So as you see, I will discuss the use of generative neural networks, both in what is called projective quantum Monte Carlo and also in classical Monte Carlo. So in fact, I will first discuss quantum systems and quantum Monte Carlo simulations. And the second part of the presentation, instead, I will switch to classical systems and classical Monte Carlo. In fact, to be honest, this is my very first project where I set h bar equal to 0. Okay, so far I had always been working in quantum system, actually in deeply quantum degenerate systems, in particular ultra cold atoms. And but the two parts of this presentation, the first one on quantum Monte Carlo and the second on classical, so they have a lot in common. Not only the use of generative neural networks, but also the kind of systems that we are trying to address and the underlying motivation. So in both cases, we will consider disordered spin models. Okay, and the interest in this kind of models is actually, it comes from the field of, let's say, we can say adiabatic quantum computing, but more specifically quantum annealing, where we are trying to understand if quantum effects can help in solving hard optimization problems. Okay, and both of these studies, they have an underlying motivation that is related to that, and I will try to explain you why. What we do is motivated by the research that is going on in the field of adiabatic quantum computing, in particular quantum enhanced optimization. So I will start discussing how you might exploit quantum effects to solve a classical optimization problem. Well, here this is a slide to explain the basic idea of quantum annealing. Okay, now here we have in mind that quantum Hamiltonian, which is composed of two parts, one here highlighted in green and the other in red. The first one, the green one, will be essentially a classical spin model, an Ising spin model. If these sigmas were just binary variables, let's say plus or minus 1. And for a computer scientist, this will be what is called the Kubo problem, so a quadratic unconstrained binary optimization problem. So in that case, the optimization problem will be to find the configurations of these binary variables, let's call them spin, okay, that minimizes this classical energy. Okay. Now, probably many of you are familiar with the idea of simulated annealing, where one performs a stochastic simulation, introducing artificially thermal fluctuations and trying to exploit these thermal fluctuations to explore a configuration space, hopefully escaping energy barriers, and so escaping from local minima and hopefully reaching the absolute minimum. So here,
if I may ask a question,
of
if
course,
it's all right with you.
Yes.
So if it's a classical Ising model, what's sigma x?
Sigma x. Okay, now we make it quantum by introducing this second part of the Hamiltonian. Okay.
Right. So these are Pauli matrices.
Yeah, Pauli matrices, yes. So they will be classical variables if you had only this green, the Hamiltonian in the green part, in this green square. Because in that case, you might choose an appropriate basis, the one of the eigenstates of the sigma z operator. And so you could see in that basis this Hamiltonian as a classical Ising Hamiltonian. But if you introduce a Pauli matrix which does not commute with the sigma z matrices, if you have, for example, a transverse field, so you have sigma x, then of course you are introducing quantum effects. Okay. And so the idea of quantum annealing is just to introduce actually a very large transverse field. So gamma, the intensity of this transverse field is very large. Okay, and then you might anneal it slowly to zero. Okay, using whatever protocol that you might choose, like the one sketched here. Okay. So at the very beginning of this process, if this gamma is huge, much larger than all of the other couplings that you have in the Hamiltonian, these coefficients Jij and also these Hi, then you will have a trivial ground state where all spins align with the magnetic field. Okay? And if you anneal this transverse field gamma slowly enough, okay, you might hopefully at the end of the process where gamma is equal to zero, then if you remain in the ground state, you should find the ground state of the classical part of the Hamiltonian. Okay, so you have solved your binary optimization problem. Now, the big question is how slow you have to be sure that you remain in the adiabatic ground state. Okay, and here you have a sketch that gives you an idea. So here I'm showing the instantaneous eigenvalues of the time-dependent Hamiltonian. Okay, now they will vary, and you don't know how. And the bottleneck will be the smallest gap that you find along the path. Okay, so the smallest energy distance between the ground state and the first excited state. Okay, and there is a theorem that tells you, it's called Adiabatic Theorem, that if the total annealing time is much larger than this time given here, so a coefficient that we don't care about, but it's a time that should scale like the inverse of delta squared, where delta is the smallest gap. So if this time, the time that you need to perform this annealing is much larger than that time, then you are guaranteed that with high probability you remain in the ground state. And so you find the classical lowest energy state, and you have solved your optimization problem.
And what's alpha here, if I may inquire?
Alpha is a coefficient. If you want to know how you will compute it, you can look at this more complete formula written below. Okay, it's a matrix element of the derivative of the Hamiltonian. Okay, here alpha I just wrote a coefficient that for the moment we are not interested in, because what is relevant for us is understanding the relation between the time that you need and delta. Okay, so you understand that the bottleneck is the smallest gap that you find along the path. Okay, so if you have, for example, if you cross a phase transition, you expect that you have a gap which is very small, a gap which decreases exponentially fast in the system size, and so you have a hard optimization problem because you expect that you need a very long time, a very long annealing, a very slow annealing, to be sure that you actually remain in the ground state and you don't jump to an excited state. Okay. Now, there is a Canadian company called D-Wave that has implemented a quantum annealer. It's also called a Adiabatic quantum computer, but it's a special purpose quantum computer that is designed to address only the binary optimization problems. And it tries to exploit it using this quantum annealing process that I have just described. Okay. Now, the big question that doesn't have an answer yet is whether such a quantum annealer, even if it was perfect, can outperform any classical optimization method that one might implement. Okay, so there is no a clear answer at the moment. Now, for me, this problem is interesting because this kind of Hamiltonian is a Hamiltonian that can be simulated using quantum Monte Carlo algorithms, because there is no negative sign problem. Okay, so nowadays people call this kind of Hamiltonians stochastic Hamiltonians. So they are the Hamiltonians that we can simulate or using quantum Monte Carlo methods without having a sign problem. For example, that's like simulating bosons instead of simulating fermions. Okay. Now,
so for you, so all J's are ferromagnetic then?
No, well, you can perform this is an easy model, so you can perform a simulation without sign problem for any type of couplings. Okay, so even they might be both
what
positive.
is sign problem then?
Sign problem, actually, I will then mention it later. Okay, so that's a tricky question because there are different definitions of sign problem. I will mention the one that is relevant for me here. At the moment, well, that will be clear in a minute, hopefully. So there is actually an equation that will help me giving the answer. Okay? But essentially, that's when you can implement, well, that one possible definition is that you have a basis that you know, where your Hamiltonian expressed in that basis has only negative or zero off diagonal elements. Okay, so that there is no positive diagonal elements. This is a case. This is the case for this Hamiltonian here. Now, here I have a slide where I have introduced a very simple easy model that is relevant for us because we will try to understand whether, let me go back, whether quantum Monte Carlo can tell us something about the possible efficiency of a quantum annealer. Okay. Now, you might be familiar with the fact that quantum Monte Carlo methods are powerful methods to simulate quantum systems, at least their equilibrium properties, for example, their ground state properties, so zero temperature, okay, but not the dynamics of quantum systems. Okay. And so far, when I have spoken about quantum annealing, I have described a dynamical process. So it's not clear whether quantum Monte Carlo can really be useful. On the other hand, it is virtually impossible to simulate the dynamics of these easy models for large systems with at least, let's say, hundreds, if not thousands of spins. Okay? This means that these quantum computers are being produced without having a benchmark, okay? Because you cannot perform the exact dynamics. And in fact, the quantum Monte Carlo methods are being used as a benchmark for these kind of machines. Okay, and now we will try to understand whether this makes indeed sense. Okay, now in some cases we will see that it does, and here you have a model where we can make some comparison. This is a very simple one-dimensional ferromagnetic easy model. So here we are indeed in the case where the couplings are all, so here J is positive. Okay. And this is in one dimension, it is a exactly solvable model, so it's very familiar to condensed matter physicists. There is a quantum phase transition from a paramagnetic to a ferromagnetic state as a function of the intensity of the transverse field. And when you are in the ferromagnetic phase, you expect to have an effective double well energy landscape, okay? Because in the thermodynamic limit, you will have two degenerate ground state with two where the spin symmetry is broken in the two directions, up or down. Okay, and in a finite system, actually these two ground states are coupled. Okay, and you might have tunneling events between these two states with the two opposite magnetizations. Okay, so here the magnetization plays the role of an effective reaction coordinate. Okay, and you expect to have a double well energy landscape. Okay, so the question now, so you see this is a type of scenario where you have a tunneling phenomenon. Okay, and tunneling is indeed probably the measure resource that a quantum annealer can exploit to solve an optimization problem. Okay, so you might believe that quantum annealers might outperform classical optimization methods because they can exploit quantum tunneling. So here we will try to understand how tunneling happens in this kind of simple model where we know what kind of energy landscape we have, and we know that there are two equivalent minima, and we expect to have a tunneling between these two minima. Okay. Now, in this case, we know that there will be an exponentially small energy gap. Okay, so the gap between ground state and first excited state will scale exponentially with the system size. Okay. And this problem has been analyzed first by the authors of these papers here. Okay. And indeed, they studied the tunneling dynamics within a quantum Monte Carlo simulation, and they compare that with the scaling with the system size of the inverse of the gap squared. Okay, so here you have three data sets with three colors, and each data set is actually double in the sense that you have open and closed symbols. You might not even be able to see the closed symbols. Okay, so the open symbols, they represent the tunneling time within a type of quantum Monte Carlo simulation performed with an algorithm called path integral Monte Carlo. While the closed symbol, they represent, again, 1 over delta squared with an appropriate coefficient which is just being fitted. Okay.
And time, the vertical axis is what? It's Monte Carlo time?
Is Monte Carlo time. So it's a quote-unquote time is just a number of Monte Carlo steps.
So it's not inverse temperature, it's not Matsubara time, it's just the number of MC steps.
Exactly. So it's a time with big quotation marks. Okay, but so the question that these authors have tried to address, and they gave an interesting answer, is that indeed this quote-unquote time, so this number of Monte Carlo steps, does indeed scale as the time that a quantum annealer will need to perform this correctly this tunneling transition. Okay. So in this case, it will look like quantum Monte Carlo can efficiently simulate the tunneling dynamics of a quantum annealer. Okay, I might mention here already that if you perform a path integral Monte Carlo with open boundary condition in imaginary time, you even get a better scaling, 1 over delta instead of 1 over delta squared, which will mean that the quantum Monte Carlo simulation is even faster in tunneling. Okay. Now, of course, this is a very specific configuration where we just have the tunneling between two competing minima, but it gives a hint that a quantum annealer cannot outperform quantum Monte Carlo.
But if I may ask one more question,
Sure.
Unless I'm asking too much.
No, go ahead.
So if you switch the Monte Carlo algorithm, then the meaning of time will be very different. So then the statement is that it still scales as 1 over delta squared. If I do path integral, or if I do SSE, for example.
So different quantum Monte Carlo algorithms can give different results. For example, here we discussed in the plot, we have data for standard finite temperature path integral Monte Carlo with periodic boundary condition in imaginary time. Indeed, if you use open boundary condition, is 1 over delta. We will see that again, if we use instead projective quantum Monte Carlo or SSE, it might be different. But again, you should always have in mind that you should use an algorithm without exploiting the knowledge of the double well structure, because here we know that the effective potential energy landscape has this double well potential energy structure, and so. But you should not use that knowledge because that will not be fair. So you should try to imagine a situation where you are trying to solve an optimization problem and you don't know the energy, how the energy landscape is.
And if I use something like stochastic series expansion with, say, periodic boundary conditions, should I expect 1 over delta squared, or we don't know?
We don't know. We don't know. This has not been tested yet, and there is no theory, I guess. Okay. Here there are semi-classical theories that justify this 1 over delta squared. And actually we did develop an analytical theory for projective quantum Monte Carlo. I will not discuss that in a minute in this talk, but I have a reference later on, so I can highlight that.
I mean, in classical Monte Carlo, it seems if you do single spin flip, it will be long. If you do some cluster updates, it will be of order 1, probably.
Yes, cluster updates, I mean, you might use it for a ferromagnetic model. Here, of course, what is being done is something that should be general enough so that you can apply to a generic optimization problem, for example, where you have random frustrated interactions. So in that case, of course, there are also in that case sampling algorithms that might help. And actually, in the second part of the talk, I will speak a bit about that. But here we are still discussing quantum Monte Carlo. Okay. Then some employees of D-Wave introduced a model. They called that Shamrock Model. It's represented here on the left. And this is a model where actually they predicted and they observed that instead path integral Monte Carlo has a pathologically slow tunneling dynamics. Okay, so this is a Shamrock model where you have a spin in the center and you have an antiferromagnetic interactions here in the between the outer spins on the leaves, and all spins are coupled ferromagnetically with the one in the center. Okay. In that case, they predicted and observed numerically that the tunneling time of the path integral Monte Carlo with periodic boundary condition imaginary time scales like 2 to the k divided by delta square, and k is the number of leaves in this model. So this is at least an example where the quantum annealer will be expected to outperform the tunneling dynamics of path integral Monte Carlo. What we did is just to perform another type of quantum Monte Carlo. I call it projective quantum Monte Carlo. It could be called diffusion Monte Carlo. Sometimes it's called green function Monte Carlo. And we have seen that that type of quantum Monte Carlo is not affected by the topological obstructions that are instead affecting the path integral Monte Carlo. Okay? So this gave us an idea that projective quantum Monte Carlo is a relevant benchmark to be compared with quantum annealers. But this also raised some other questions. Okay, now we said at the beginning that when we don't have a sign problem, we expect to be able to perform quantum Monte Carlo, let's say easily. Easily will mean with a polynomially scaling computational time, I mean polynomial in the system size. But this probably cannot be always the case, okay? Even for Hamiltonians that do not have a sign problem. Okay? In fact, this was pointed out, for example, in this paper here. I mean, any diagonal Hamiltonian, like the one that we highlighted with the green color, okay, this one, well, this is stochastic, so it's an Hamiltonian without a sign problem, if you see it from the point of view of quantum Monte Carlo. Still, finding its ground state includes relevant NP-hard optimization problems. Okay, so it cannot be possible that quantum Monte Carlo is always efficient in the cases where you don't have a sign problem. Okay, there must be problems even in that case. Even in the absence of a negative sign problem, there must be some potential problems with quantum Monte Carlo. Otherwise, that will mean that with quantum Monte Carlo, we could solve NP-hard problems. And so we can go back to the theory of projective Monte Carlo and see if there are possible drawbacks, okay, possible flaws. And there is indeed, and they are actually well known. I will just highlight them here. Okay. Now, when you perform projective Monte Carlo, essentially you are evolving a large populations of what people call random walkers. Okay. And these walkers, they undergo a sort of random diffusion. Okay, but sometimes then they are killed and sometimes they are replicated. So there's a sort of genetic algorithm, if you wish. Okay, but then you have to control the total size of the population that you have, such that it doesn't go to zero and it doesn't explode. Okay, and it is known that this population control can introduce a bias. Okay, it's not known exactly how large this bias is, and so we did reanalyze it here to understand what is the fundamental level, the computational complexity of performing a projective quantum Monte Carlo simulation of an Hamiltonian that does not have a negative sign problem. Now here you have some theory of projective quantum Monte Carlo. Essentially, you are evolving the Schrödinger equation in imaginary time. And here you have a pseudo Markov process, let me call it like that, where you have a Green's function, which is defined by the exponential of minus delta th, and delta t is a short imaginary time step. Okay, and if you have a basis here where this matrix is real and positive, then you can perform a quantum Monte Carlo. So there is no negative sign problem. So this is a possible definition of absence of negative sign problem. But there is another problem. Okay, so this matrix can be positive, so you will have what can be called a stochastic Hamiltonian, but this is not a stochastic matrix in the sense that it is not column normalized. Okay, we know that in order to define a Markov chain Monte Carlo simulation, you need a stochastic matrix. Okay, so the sum of the numbers on the columns of the transition matrix of your Markov chain should sum up to 1. Okay? And that's why we have to introduce this sort of genetic algorithm. Okay, so this absence of normalization is taken care with the proper algorithm by introducing this, by killing or replicating walkers. Okay? That's the origin of the potential bias in projective quantum Monte Carlo simulation where there is no negative sign problem. Okay, is this condition of normalization which is missing. So if we perform that in the projective quantum Monte Carlo simulation in this simple form, which I have just explained, and that's not how we usually do it, but let's suppose we do it, we indeed will see an exponentially scaling computational cost. Okay, and we will see it like this. Suppose that you choose a large population of random walkers such that the bias that you have is below the threshold that you choose, okay? And then you increase the system size, okay? You will see that the number of walkers that you need increases exponentially with the system size. Notice that here on the vertical axis, I have a logarithmic scale, okay? So performing a projective quantum Monte Carlo simulation in general has an exponentially scaling computational cost even in the absence of a negative sign problem. Okay? But that's where neural networks can come in. Okay? So in general, we never perform projective quantum Monte Carlo using this simple algorithm. We will always introduce what practitioners call importance sampling, which in this case will mean that we introduce what you might call guiding wave function. Okay? This is just a variational ansatz. It's also called trial wave function. Okay? Here I call it psi g. Okay? And we modify the Markov process using this random walk, this trial wave function or guiding wave function. Okay? I could show, I'm not showing this here, that if this trial wave function was exact, okay, if I knew already the ground state wave function, even one random walker would be enough to obtain an unbiased result. Okay, so in general, I can expect that if this is not exact, but it is a reasonably accurate variational ansatz, I would reduce the bias originating from this population control. Now, the problem is being able to build a general variation wave function for example, for random spin models relevant for combinatorial optimization problems. Now, here, that's where you might introduce a generative neural network. For example, you might consider a restricted Boltzmann machine. This has been used by several authors in recent years to build variational wave functions. So the idea is that you want to introduce correlations among your real or visible variables here in the lower layer in yellow. This could be the spins of your model via auxiliary hidden variables. Okay, and then you can write an energy function of the full system. Okay, and following the standard strategy in deep learning, you will introduce connections only between different layers. That's why it's called restrictable machine, because you don't have interactions between spins belonging to the same layer. You have only connection between different layers. Okay. Now here you might see that this type of neural network is designed to approximate a probability distribution. Okay, and I will see why in this case, even if we are dealing with quantum systems, that's possible. Okay. But so when you use a restrictable machine, the probability of a visible configuration will be the marginal probability distribution where you integrate out the hidden variables. Okay. Now, this type of model has been introduced as a variation wave function in this work by Carleo and Troyer, and then many others followed using the same type of generative neural networks or deeper neural networks. Now, here I would like to mention that, in fact, the idea of building variation wave functions using hidden variables to introduce high-order correlations between visible variables is not new to physicists. In the late 80s, researchers working on helium, in particular liquid or solid helium, used what they called shadow wave functions to try to build a variational ansatz that could describe a potential supersolid, so a system that breaks translational symmetry without breaking the bosonic symmetry for particle exchange. And they introduced what they called shadow wave functions. So they had shadow variables instead of hidden variables, but they play a similar role. The big difference that in that approach, you have interlayer connections between visible and hidden variables with the same index, but you have also intralayer connections, okay, that you don't have typically in neural networks. Okay. Now, we'll show you that with this type of structure, even with very few variational parameters, you can obtain a variational ansatz that is very good to be used as guiding wave function. Okay. Here I have just one example. I don't want to highlight this work. I just want to show you that if indeed you take that variational ansatz and you use it as guiding wave function in your projective quantum Monte Carlo simulation, you go from this exponentially scaling computational cost to a computational cost that is polynomial in the system size. Okay, so that's just to show that a good variational wave function can drastically increase the efficiency of your projective quantum Monte Carlo simulation, such that you obtain essentially unbiased result with a polynomially scaling computational cost. Okay.
Again, if I may inquire, I'm probably asking too many questions.
No, it's fine for me. It's fine. I like it.
But how do you fix the parameters of this wave function?
Yeah,
so
that's a very
by bunch of parameters.
Yes, indeed, that's a very good question. So here I have described this shadow wave function because it's a simple variational wave function with very few parameters. Okay, so I cannot use any variational Monte Carlo scheme to optimize them. Okay. Now, a more complicated question is when you use a restrictable machine where you have an all-to-all connectivity between different layers. Okay. This is what machine learning practitioners will call dense neural network. Okay. Now, in this case, you have a huge number of variational parameters. Now, again, you could use variational Monte Carlo and perform amortization like with stochastic gradient descent. And that's what Carleo and Troyer did. Okay. But that's, of course, another optimization problem. Okay. So optimizing the variational parameters the parameters of a neural network is a hard optimization problem. There are many algorithms to do that, but there's no guarantee that you will have success and find sufficiently good parameters. Indeed, here, what I want to describe here is actually a scheme where the optimization of this parameter is more automatic. And let me explain in what sense. So a restrictable machine can be trained also via a scheme that would be called unsupervised learning. Okay, so if you have random samples, okay, so configuration sample from whatever probability distribution, typically a restrictable machine will be used to infer the underlying probability distribution from which the samples that you have been sampled from. Okay. Now here you have the algorithm, a sketch of the algorithm. I don't want to explain in detail. The key idea probably is this equation here. So it shows that what you are trying to do is to optimize the parameters by optimizing the logarithm of the likelihood of the samples that you have. Okay. This is equivalent to minimizing the so-called KL divergence, Kullback-Leibler divergence. This would be the divergence, so a measure of difference between the underlying distribution of the samples that you have and the probability distribution associated to the restrictable machine. Okay. So what we did is to implement what we call self-learning quantum Monte Carlo. It's a Monte Carlo scheme where you start performing a projective quantum Monte Carlo simulation. You generate samples, and then you use those samples to train a restrictable machine. And then we use the restrictable machine as a guiding wave function in the next quantum Monte Carlo simulation. And we repeat that process. So what you get is a scheme like this, okay? So in general, when you perform a projective quantum Monte Carlo, the samples that you have, your random walkers, would be sampled proportionally to the product of your guiding wave function, which is the variational ansatz that you have, and the true ground state, which is unknown, but your algorithm samples from that accordingly, proportionally to that function, okay? So since we are dealing with a stochastic model, so a model without a sign problem, we know that we can choose the ground state wave function to be a real and non-negative function. Okay, so this scheme is restricted to stochastic models, so to models where there is no negative sign problem. Okay, and so the idea is that you train your restrictable machine, and then you take the square root of the probability distribution that you got as a guiding wave function for the next run. Okay. So here I have a plot that gives somehow the idea of how the simulation works and why it is efficient. Okay. So here in green, you will have a simulation that is performed without any guiding wave function. This is a very naive algorithm that actually no one would use. Okay, and you see that the energy that you get is biased. Okay, so here the exact result is given by this black horizontal line in the bottom, and it cannot be obtained for this model. Here the model is a ferromagnetic quantum Ising chain at the ferromagnetic quantum critical point. And the result can be predicted analytically using so-called Jordan-Wigner theory. Okay, that's an exactly solvable model, and we use it because we have analytically exact result. But it's still an interesting model because you have a quantum critical point. Okay? In general, simulating systems at criticality is not an easy task. Indeed, if you do it naively, you get this green result and you see a huge bias due to the population control. Okay? Then if you use our self-learning quantum Monte Carlo, at the beginning we do have a bias, but then stint after stint, so segment of simulation after segment of simulation, your guiding wave function improves, okay, and very early, very soon, it becomes good enough such that any bias that you might have had completely disappears, okay. And you obtain an unbiased result with very, very small statistical fluctuations, okay. And here in blue, you see also the expectation value of the Hamiltonian operator that corresponds to the ansatz that you are building automatically. And you see that it improves. Okay. Of course, there is no guarantee that it will converge to the exact result because, I mean, we do have a neural network, which is a rather flexible model. But of course, we have a finite neural network with a finite number of hidden variables, and there is no guarantee that that function can approximate the ground state wave function that we have. You would have a guarantee that in principle, this neural network could approximate any function for an arbitrarily large number of hidden variables. Okay, but with a finite number of hidden variables, that is just a very flexible ansatz, but it might not be able to perfectly approximate the ground state wave function. Okay, so the last result for the first part of the talk that I want to discuss is just an application to a slightly more challenging model, which is a random Ising chain. So again, it is a one-dimensional model, but with random couplings. Okay, so it's more challenging because we have disorder. We still have a quantum critical point, but it's still an unfrustrated model in the sense that it's one-dimensional and we only have nearest neighbor interaction. Okay. Now, what we did here that was interesting for us was trying to explore different type of connectivity structure in the neural network. Okay, the standard one will be this dense connectivity where the visible variables are connected to all hidden variables. But for a physical system, which you might expect has mostly, not only, but mostly nearest neighbor correlations, or at least finite range correlations, you might expect that the connectivity where a visible spin is connected only to, let's say, 3 hidden variables might be more adequate, more efficient. Okay, and indeed we saw that this is indeed the case. Okay, in the sense that with a much smaller numbers of parameters to be optimized, we obtain accurate results. Okay, so here, for example, in this plot on the top right, we have the number of connections. Okay, and we see with the full symbols the results that we obtain with sparse connectivity. Okay, and the empty data, the empty symbols, are what you would obtain if you have a dense connectivity and you vary on the horizontal axis the number of hidden variables. Okay, so you see that with the sparse connectivity, you need a smaller number of connections to have a very accurate variational ansatz. Okay. Again, here we have the results of projective Monte Carlo for many instances of the disordered Hamiltonian, and we are plotting the relative error of the prediction of the quantum Monte Carlo simulation compared to the Jordan-Wigner theory, and we see that the results are absolutely unbiased, and there are also only very small statistical fluctuations, sometimes positive, sometimes negative, but they are just random fluctuations, and they become, even this fluctuation becomes smaller and smaller when we increase the connectivity in the neural network. Okay. This just to give an idea that it is worth exploring optimal neural network structures with optimized connectivity structures for specific quantum systems. Okay, there's no reason to believe that what has been found to be effective in machine learning, that is dense connectivity, is also very good to describe quantum systems. Okay, now we'll switch quickly to the second part. It will not be very long, so it will not take too much time, but it might be interesting. So now our idea is to simulate classical spin glasses. And so indeed now we do have just binary variables, which are either +1 or -1. And we will consider a two-dimensional spin glass model on a square lattice. Okay. Now, it is well known that simulating these models with naive classical Monte Carlo algorithms, like the single spin flip, becomes impractical when you go to low temperature. Okay. Now, this model in 2 dimensions is actually now known to have a proper spin glass phase only at 0 temperature. Okay. But if you look at the literature, there is a temperature which is of the order 1. Okay, if you have Gaussian couplings, as we do here, Gaussian couplings with standard deviation equal to 1. And at this temperature has been called in the literature freezing temperature. Okay, now it is known not to be associated to a proper spin glass transition, but it is a freezing temperature in the sense that the classical Monte Carlo becomes pathologically inefficient. Okay, and here we have performed a simple exercise of computing the autocorrelation function along a classical Monte Carlo simulation of a trivial observable like the energy. Here there's a typo, this M should be an E. And we see that when you reach the temperature 1, the autocorrelation time becomes exceedingly long. Okay, and so, but this is well known, and no one would use this simple single spin flip algorithm to perform the simulation of a spin glass in the low temperature regime. There are many more powerful methods, like parallel tempering is one, replica exchange, and there are many others. Okay, I will not discuss those. I will discuss the possible use of autoregressive neural networks. And again, you will see that we do this with a possible connection with the use of quantum annealers. Now, here we will not use the restricted Boltzmann machine for a couple of reasons. First is because when you have a restricted Boltzmann machine, you do not have a normalized probability distribution. You have a partition function that cannot be computed for large systems, so it's intractable because you should sum over all configurations. And in order to generate a sample from a restricted Boltzmann machine, well, you have to perform a Markov chain Monte Carlo simulation. Okay, that is doable, but again, you have no guarantee on how long the autocorrelation time will be. Okay, and again, if you have a glassy system, like you have usually when you deal with optimization problems, okay, you expect to have, again, long correlation times. Okay. Now, the solution would be to introduce the so-called autoregressive property. Okay. So in this case, you will want to have a neural network which allows you to approximate a probability distribution, okay, using obtaining a chain of conditional distribution. Okay. Here I have to apologize again. There's one typo, so this V should be an X. Okay, I changed notation a couple of times in these slides, and I will correct these typos before sending you the slides. But just think about this V that should be an X. And so what you want is that the probability of a given configuration, so this X with the bold character is a vector of spin variables. You would like to write the global probability as a product of chain conditional distributions, where the probability distribution of a given spin, okay, let's say the spin number D, only depends on the previous spins. Okay, so for example, the fourth spin should be affected only by the first, the second, and the third. Okay, if you have this property, you can create exact samples directly using so-called ancestral sampling. Okay, so you start sampling your spins one by one. You start with the first. Then once you have the first, you can sample the second because you have the conditional probability distribution, which depends only on the first. Then you go to the third, knowing the values of the first two, and so on and so forth. Okay, you create a direct sample, okay, without using a Markov chain. Okay, now there are neural networks that allow you to do that, and the simplest one has been introduced by La Rochelle and Murray in this old paper. And this neural network is called NADE, Neural Autoregressive Density Estimator. It has this kind of structure. I will just sketch a couple of details of the structure. So here you have your visible variables. Now here I use the letter V. Okay, and you have a number of parallel hidden layers. Okay, and the number of these parallel layers is equal to the number of visible variables. Okay, but you should notice the possible connections. Okay, so for example, the hidden layer 2 is only connected to V1. Okay, while the hidden layer 3 is connected to V1, V1, and V2, and so on and so forth. Okay. So here at the output, you should have the probabilities, the conditional probabilities of sampling the variable up or down, or +1 or -1. And you see that you have this the autoregressive property that I have described before. Okay, so in order to sample one variable, you need only the knowledge of the previous variable in the order that you have chosen. Okay, so how can you use this kind of autoregressive neural network within classical Monte Carlo? Okay, so our idea is that you can generate somehow a sample of configurations. Suppose that you are able to perform a first good classical Monte Carlo simulation, and we will see how to do it. Okay. Once you have your samples, you can train your autoregressive network, and the goal is to have that the probability associated to your neural network approximates the Boltzmann distribution. Okay. Again, this is done by maximizing a log likelihood, and again, this corresponds to minimizing a Kullback-Leibler divergence. Okay. Now, the samples that you use to train your neural network, they could come from a previous Monte Carlo simulation. They could come from what we call sequential tempering. In a minute, I will describe what it is. But in principle, they could be generated using a physical quantum annealer, like one of the quantum computers built by D-Wave. Okay. Now, once you have trained your model, what will you do? Well, you can use directly the model to generate samples and compute the expectation value of the energy on the probability distribution that corresponds to the neural network. Okay. Hopefully, if your network was trained well, that should be close to the thermodynamic value. Okay, so what will correspond to the probability, the Boltzmann probability distribution. But what we did is something that might be more useful. So what we did is to use the generative model, the autoregressive generative model, to propose new configurations for the Metropolis Hastings algorithm. Okay, that is the here you have the standard formula for the acceptance probability in the generalized Metropolis Hastings algorithm, and we use the probability distribution corresponding to our neural network as a proposal distribution. Okay. You might notice that here, if your the probability distribution associated to the model is indeed close to the Boltzmann distribution, then your acceptance probability is close to 1. Okay. In the ideal case where the two probability distributions are the same, then you have perfect samples, the dream of all Monte Carlo practitioners.
But that's a global update, right?
That's a global update, yes. You just generate a new sample, and notice there is no information on the old one. Okay, so the only correlations that you might have come from rejections. So it's a totally global update, as global as possible. Okay. Now, here you have a test. This is one instance of a 2D model with a moderate size. So we are here playing only with 100 spins. So it's a 10 by 10 model at the inverse temperature beta equal 1. That's already a regime where the single spin flip algorithm will not work. Okay, and see what happens. So here on the horizontal axis, we have the number of hidden neurons in our autoregressive model. And you see first that indeed the expectation value of the energy over this probability distribution, well, it converges, it goes very close to what you would get with a good Monte Carlo simulation at thermodynamic equilibrium. Okay. But more importantly for us is that when you perform the Monte Carlo simulation using this model as smart proposal generators, you always get results which are statistically compatible with the exact result, as they should. Okay. In fact, increasing the number of hidden neurons only increases the efficiency of your simulation in the sense that the acceptance rate increases. Okay. If you have very few hidden neurons, of course, your model is not very flexible it will not approximate well the Boltzmann distribution. Okay? So you have a terrible simulation with a very, very small acceptance rate. But if you have a sufficiently complex neural network with many hidden neurons, you might train it well enough such that your acceptance rate becomes substantial. Okay. Now, then the problem and the question might be, but okay, here you have assumed that in the very first step, someone gave you good samples, okay, good configurations, which were sampled from the equilibrium probability distribution, and you use that to train a neural network, okay? But performing a simulation, a Monte Carlo simulation for a low temperature spin glass is inherently difficult, okay? And here we introduced a technique which we call the sequential tempering, of course, in analogy with the famous parallel tempering technique, okay? So the idea is to start from a high temperature when whatever Monte Carlo algorithm works well, okay? You perform a simple Monte Carlo simulation, you generate configurations, you use those to train a neural network, and then you use that neural network at a slightly lower temperature. Okay? And then, of course, you reperform a Monte Carlo simulation, now using the previous neural network as proposal generator, okay? And you resave configuration, and then you retrain a neural network. And you have to perform a sequence. And we see that if you do that, the acceptance rate when you go from high temperature to low temperature doesn't actually decrease, it even increases. And we have observed that we can perform very efficient simulations also in the regime of relatively low temperatures. Okay. And here to highlight the efficiency of the algorithm, we have an example of a simulation performed at beta equal 2, which is already a low temperature. Okay. And we see the outcome of the Monte Carlo simulation driven by the neural network, the autoregressive neural network. Okay. And you see that the simulation is basically at equilibrium from the very beginning. And here you see with the blue line, the blue horizontal line, the ground state energy, so the energy of the optimal configuration. We obtained that from the spin glass server from the University of Cologne. And you see that the simulation driven by this autoregressive network very frequently and rapidly touches the ground state. While if you perform at this temperature a naive single spin flip metropolis algorithm, you have divergingly long autocorrelation times, and the thermalization is outrageously long. Okay, so this shows that if you perform this sequential tempering procedure, you can arrive at low temperature and perform an efficient Monte Carlo simulation that, interestingly for us, is also good to sample to find the lowest energy state, which is in itself a challenging problem. Okay. Now, I will in the last 30 seconds, highlight the very last result, which is still work in progress. And so this result should be taken with caution because we are still analyzing the data. So as I have mentioned a few minutes ago, our idea will be to combine this kind of techniques with physical quantum annealers. Okay. Of course, physical quantum annealers are not perfect. Okay, so you should expect to have noisy data. Okay, you might have two kinds of noise. Okay, the first noise is that when you implement your Hamiltonian on the physical quantum annealer, probably you're not going to implement exactly the model that you wish, but there will be some noise in the couplings that define the Ising Hamiltonian. Okay? Or you could have errors in the reading procedure. Okay? So maybe your model has been implemented perfectly, you get the samples out of the machine, but sometimes in the reading procedure, you have a reading error. So with a certain probability, instead of reading the spin up, you read the spin down. Okay? So here we analyzed how detrimental are these random errors. Okay? So in the plot on the left, we have added some Gaussian noise to the couplings, okay? And sigma is the standard deviation of the noise. And you see again that the noisy Monte Carlo simulation is of course biased. That's the black data here. But even if you train a neural network on, let's say, noisy data, okay, that is of course a neural network which is learning the wrong Boltzmann distribution. Okay, the Boltzmann distribution corresponding to a wrong model. But if you use it as proposal distribution in a Monte Carlo simulation, it's still sufficiently accurate. Okay, in the sense that the result is unbiased and the acceptance rate is reasonable. Okay. And here again, we have on the right the results that you would obtain by having errors in the reading procedure. So you have randomly flipped spins. And again, we see that the simulation performed with a Monte Carlo algorithm driven by the autoregressive network is still always unbiased, even though the energy, the expectation value of the energy corresponding to the noisy configuration deviates significantly from the exact result. Okay. Since I'm a bit late, I will just sketch the conclusion slide. Okay, I will not repeat it. And here you have some useful references in case you are interested. And with this, I thank you very much for your attention, and I apologize for going a couple of minutes long.
Oh, it's okay. Thank you for the very interesting talk. Any questions?
Well, I actually have a few, but maybe someone other than me has any.
Go on.
Vyacheslav, is that your hand?
Yep. Vyacheslav, I have a question. Can we return back to the sliders where you described this technique of using CJ? It was...
You're speaking about the classical Monte Carlo or quantum?
Quantum one.
Ah, quantum one, okay. Which slide are you interested in?
Previous of this, I remember. And another one? Yes. Well, the question is, as I understood, we use this psi-j to guide our simple psi, and we train it by neural network. And we train it with some data. And this data, the question is where we take this data.
Yeah. So in general, what people would use here for psi-j is whatever ansatz that you might have. Okay, that's a variational ansatz, trial function. You might optimize it with whatever technique you might want. Okay. Typically, people will use variational optimization. Okay, so you have an expectation value of the energy, you tune your parameter such that that expectation value gets the minimum value. Now here we did something different. So we exploited the fact that we are dealing with a generative neural network. Okay, it's a generative model that can be trained by maximizing a log likelihood. Okay, that would be the training algorithm. This is an algorithm which will be called k-step contrasting divergence. So what we did is the following. We do an iterative process. Okay? So we start the quantum Monte Carlo simulation without a guiding wave function. Okay? So we get samples, okay, which are biased. They're not perfect. Okay? But we use those samples to train the neural network. Okay? Now we have a reasonably accurate variational ansatz. Okay, it's not perfect, but we can use it. Okay, and now we use it for a second quantum Monte Carlo simulation. Okay, it's a second segment if you wish. Okay, and now this second simulation is better because we have a guiding wave function, which is not perfect, but it doesn't have to be. Okay, and now we get new samples, and those samples will be less biased. Okay. And then we can iterate the process because we always get new samples and the guiding wave function that we have becomes better and better. Okay. Now it will never become perfect, because it is just a variational ansatz, and there's no guarantee that it can approximate your ground state wave function. And even if it could, in principle, that will still be an optimization problem that maybe your optimization algorithm is not capable to solve. But here, as guiding wave function, we only need a reasonably accurate wave function. Okay, so it's not something that really has to perfectly mimic the ground state. Okay, to be honest, there is still no theory that tells you really how accurate it has to be. Okay, but here empirically, for the models that we have studied, we have seen that this type of ansatz works well. Okay.
So this is kind of self-pooling. Okay, thank you.
Yeah.
More questions?
So now, if I may ask, can we fast forward to your classical spin glass simulations, to the
Yes.
second part?
Yeah.
When you mentioned that this very smart global updates, they
Yes.
have large acceptance ratio.
Yes.
Can something be said about the correlation properties? But I mean, I can have exactly an acceptance ratio equal 1 by doing nothing at each step.
Yes, we do, and we see that the correlations become absolutely negligible. We did compute them, so we compare the correlation that we obtain with this smart algorithm with the standard correlations with the correlation that you would obtain with the naive single spin flip metropolis algorithm. We saw that, the correlations are become really negligible. We have a plot in the paper. I didn't include it in the presentation.
Oh, great, thanks. And maybe my last question before I stop. Well, I have many more, but I think I'll stop after this one. So you're looking at this short range spin glass.
Yes.
Is there any reason to look at, say, Sherrington-Kirkpatrick, which is long range, where there are at least some exact solutions, something to compare to?
Yeah, so we didn't do that exactly because the model, well, from some point of view, is believed to be easier in the sense that you have a mean field theory that is supposed to work well. So we took the short range model because it's supposed to be more challenging. Now, we could do that. A priori, there is no reason to believe that the autoregressive neural network that we have should not work well. I think we should be able to handle long-range interactions. What we think we have to do for future work is simply to go to larger system sizes. Okay, so far we have considered short ranges in models up to 250 spins, which is challenging if you use a naive algorithm, but there are already existing methods that can do that and even more. So what we should do is to test the neural networks that we employed to larger system sizes, and of course different models like Sherrington-Kirkpatrick model can be another interesting test set. Even going to 3 dimensions actually is a rather than the 2-dimensional model is a challenge. Now, and we could, in principle, use also different type of autoregressive neural networks. There are several. Variational autoencoders are a possible solution. There is a model called Pixel CNN, which has a convolutional structure and still has an autoregressive property. And so it is probably more adequate for large systems because of the convolutional structure. So that's the structure that you would use, for example, in image analysis. And so there is a lot of work to do. I think that so far we have just performed a proof of principle demonstration.
Yeah, thanks.
More questions? Okay, Sebastiano, thank you very much for a very interesting and exciting talk. I hope in the nearest future we will have possibility to talk in person, not via Zoom on that. And okay, I'll stop recording at that